Okay guys, here's our video lecture for the day. We are starting with exceptions to our octet rule. And we're going to see how some things are a little bit different when it comes to some of our elements in particular. We're going to start with phosphorus. So phosphorus is PCl5 is our example. And if we take a look, phosphorus looks like this. Now at the first glance, as you're looking at this molecule, you'll notice that coming off of phosphorus, there's 5 different bonds. Those 5 bonds then, if we do our math, correlate to having 10 valence electrons there. So 10 valence electrons is obviously more than our octet rule, which is supposed to be our valence electrons of 8. We have 10 there. Phosphorus has the ability to expand its octet. Sulfur also has that ability. So if you take a look at sulfur, our second example there, sulfur has 6 bonds coming off it, which allows it to expand its octet up to 12 electrons. Now, it does this when you're dealing with the halogens. So if you take a look at phosphorus, notice how it's phosphorus with chlorine, sulfur with fluorine. It's not just chlorine, it's not just fluorine. Those are just 2 of our examples of one that's actually doing this. So anytime you have your phosphorus or sulfur with halogens, they're able to expand their octets. Let's take a look at how that works and see why it's possible. So phosphorus, when we start off with phosphorus, it has 5 valence electrons. And we typically think, okay, we have 3 places for it to bond and 1 unshared pair, because that's been what we've been talking about in terms of our formal charges and everything. But also what you could do is, with this, you can imagine these not being paired, and instead imagine them being as locations for bonding to happen. So if we put chlorine around the phosphorus, and chlorine has its 7 valence electrons, we see that phosphorus's 5 are able to bond up with all 5 of those chlorines. Now, we should check our formal charges to make sure that there's nothing goofy going on with formal charges. Well, phosphorus starts with 5. It has 1, 2, 3, 4, 5 bonds now. We can show that by drawing in the 5 lines. So it has 5 bonds. It's a 0. Chlorine, same idea. It has 7 to start. We're going to subtract away 1, 2, 3, 4, 5, 6 unshared electrons minus the 1 bond. It's a 0. So formal charges disagrees. Everything is zeros in here. Phosphorus just has to not abide by the octet rule. Okay? This is possible because if you take a look at phosphorus's electron configuration, it ends in a 3s2, 3p3. What we sometimes forget is that there's actually a 3d orbital that's completely empty. With this empty orbital, that allows phosphorus to use some of the space in this 3d orbital to expand its octet. Okay. So for phosphorus and for sulfur, they're able to expand into those d orbital regions to allow it to bond more than just 4 times and into 5 times and 6 times for sulfur. Now if we take a look at sulfur, sulfur does the exact same thing, except for it starts with 6 valence electrons, so those ones that we typically pair up, we can space out, and it can form up to 6 bonds coming off it. And you can do something as simple as hydrogen bonding to it, or any other halogen. Okay, so hydrogen or any other halogen works for this process, where they want to create 1 bond with our phosphorus or our sulfur. Okay? These are exceptions where we are able to expand our octet. Now here's one problem. When we start dealing with the math behind this, so let's take sulfur with 6 fluorines. Mathematically, we would say sulfur wants to have a certain number of electrons, fluorine wants to have a certain number of electrons. We've always been saying that's a magic number of 8. So if we have 6 fluorines and 1 sulfur, we have 7 atoms here, which we would have taken that times 8, so we would say you need 56 electrons to start our math. Sulfur starts off with 6, fluorine has 7 times 6, so 7 times 6 is 42, 42 plus 6 is 48. We have 48 electrons. So if they want to have 56 electrons, and they actually have 48, if you do the math, that first subtraction to figure out how many are shared, you get 56 minus 48, and we get 8 for an answer, which would then tell us that we have 4 bonds. Now let's take a look at that. Sulfur with 6 fluorines. No matter how you try to do this, even if you try to make the octet rule work by fluorines coming off of fluorines, which doesn't happen, there is no way that we can only do 4 bonds here. So if you do the math and you get something that's impossible, okay, you know that you have an exception. So anytime you do the math method, if you find a scenario where it's impossible, this is impossible that we only have 4 bonds here. We have 7 atoms, so we had to have at minimum 6 bonds on here, if not more. So we know that this math is not going to work. Now there's a way to fix it. For sulfur, we assumed it wants 8 electrons. But remember, with the halogen, sulfur can go up to 12. So instead of saying that sulfur has 8 electrons, we would say that the sulfur can hold up to 12 electrons. The fluorines still hold their 8, so we have 6 times 8, which is 48 electrons. So now we have actually 60 electrons that can be used for this molecule. We still have the same number, so we still have our 6 valence electrons for the sulfur, plus the 42 for the 6 times 7 for the fluorine. So we still have 48 electrons on here. 60 minus 48 is 12 electrons. Divided by 2 gives us 6 bonds. Which now that starts to make more sense because sulfur should bond 6 times, 1 time each, to the fluorines. And then fluorine, of course, has its extra electrons on it. And we can do that math too. So 48 minus the 12, and we get 36 electrons. Or we get 6, 6, 6, 6, 6, and 6. Or 36 electrons that are unshared electrons. Okay? So for sulfur, if you're going to use the math method, you have to realize with a halogen, it's going to go up to 12 electrons, which is going to change your math a little bit. Otherwise, if you don't want to do the math method with the exceptions, just realize doing it the normal way, the exception will show itself because the math will be impossible, and then you can just figure it out by using more of a systematic approach to the bonds and the ions with it. So that's sulfur and phosphorus. Those are the tough ones. Okay? Boron, if we take a look at boron, with boron, it actually reduces its octet. So it's in group 13, which means boron only has a starting of 3 valence electrons. Well, if it only has 3 valence electrons, one of its possibilities is to bond each of those valence electrons to a halogen again. So boron will have a reduced octet, meaning it can work with only having 6 around it. Again, the math will work, but you have to realize with boron that its number is not 8. So for boron, it's not going to look for 8 electrons. Boron, we have to only give it 6. So when boron bonds with a halogen, if you want to figure out the total electrons it needs here, it'd be 8 plus 8 plus 8, or 24, plus the 6 would be 30 electrons needed. Fluorine has 7 plus 7 plus 7, that's 21, plus the 3, so that's 24 electrons that you have. 30 minus 24 is 6. 6 divided by 2 is 3 bonds. So that's why we only get the 3 bonds here. Okay? It's just remembering that boron has a reduced octet when it forms with the halogens. Okay? Again, this is something that we're dealing with when these are working with our halogens. Now, the other exception we've already talked about in class. We did it when we started talking about isomers and those kind of things, where we have an odd number of electrons. So for NO2, if you look, nitrogen has 5 valence electrons, oxygen and oxygen both have 6. So when you add them up, we get 7 valence electrons. Sorry, we get 17 valence electrons. With 17 valence electrons, one of those 3 atoms must have only 7 electrons around it. There's nothing we can do about it. It just doesn't have an even number. So in that case, use your formal charges to determine the best location for the unpaired electron, if you get a molecule that's similar to this. Oxygen is kind of a weirdo, okay? If you take a look at oxygen, you would probably assume that oxygen bonded to itself, they both have 6 valence electrons, would bond as such, giving you a double bond. That is what commonly people think. Actually, if you go online and look, you will see that this is the right answer in several websites, which is wrong. I've actually had teachers I've taught with that I've actually had to explain this to them to show them that that is not actually the way it actually works. If you look at formal charges, it lines up just right. Oxygen has 6 valence electrons, minus the 4, minus the 2, they're zeros. So this would make perfect sense that it does this. In reality, this is one of 2 possible resonance structures that oxygen does. The other resonance structure, which is abnormal, is such, where you have a single bond and 2 singles on the outside. They don't pair up. You may think, well, that doesn't make sense, which you're right, it doesn't make a lot of sense. But if you look at formal charges, we're still okay. Count those on oxygen. It starts with 6, minus 1, 2, 3, 4, 5, minus the 1 for the bond. Our formal charges still agree that we have 0 here. So going back to the rule of formal charges, there's no reason why this can't happen. Is the octet satisfied? Well, let's see. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the octet rule is not satisfied here. That's why we call it exception to the octet, where these do not have 8 for each one. It's an oddity. It's something that's weird in our universe. Now, we've been able to experimentally prove that this happens. And to do that, we need to talk a little bit about magnetism.
This magnet is very strong. The poles of the magnet...
Okay, we're happy the magnet's very strong, but let's talk about it before we get to the video. When you're dealing with magnetism, we have 2 different terms that we use when it comes to things that are not magnetic. Okay? The magnets you're thinking of that hold pieces of paper to your refrigerator and do those kind of things, those are called ferromagnetic. They're actually magnetic themselves. They create magnetic fields Okay, those are like the metal magnets you played with in Earth Science class, the North Pole, South Pole. That's your typical magnets. However, molecules respond to magnetism in one of two ways. If they're diamagnetic, meaning everything is paired up, they actually will repel themselves away from a magnetic field. So if you have a gaseous state or a liquid state, they will actually push away from a magnetic field slightly if they're all paired up. If they have one or more unpaired electrons, they're paramagnetic, we call that. When that happens, the molecule actually attracts itself very strongly to a magnetic field. So what we're going to see in the video is oxygen exhibiting paramagnetism. Okay, they're going to start with nitrogen, and then they're going to move on to oxygen. We're going to compare how those work. Nitrogen is not paramagnetic. So nitrogen is diamagnetic. Where oxygen, because of this oddity, is paramagnetic. So we would assume that this would repel from a magnetic field slightly, not a massive amount, but just a small amount. And the oxygen, we would see that it should attract. That's not attack, attract. Attract to a magnetic field. Okay? So, let's take a look on the video.
Are 1 centimeter apart. Focus your attention on the poles of the magnet. The Dewar flask or thermos contains liquid nitrogen at a temperature of 77 kelvins.
Notice how the nitrogen here, it's not sticking between the magnetic poles. It's almost like splashing away from those magnetic poles, almost like it's trying to get away from it.
The test tube contains liquid oxygen at a temperature of 90 kelvins.
So see the difference here? The liquid oxygen actually gets suspended between the two magnetic poles because it's being attracted to those. And instead of falling through and splashing away, it's actually attracted to that magnetic field, showing paramagnetism. So it's a way to experimentally support and prove that oxygen has this resonance that isn't kind of an oddball or a different than what you'd expect it to have. And of course, it evaporates very quickly because it's so cold compared to the environment.
The residual white solid is ice, which formed from water in the atmosphere.
So this white stuff they're talking about here and up here, that is basically moisture in the air that got frozen in the process of dumping out the liquid oxygen on there. Okay, so oxygen, we get back to it, is just an oddball. It's one of those you're just going to have to memorize, that it's different than what you'd expect it to be. It's just not what you'd expect it to be. Okay?